Welcome back again and to continue this international conference on the zero. And I would like also to welcome and to say hello to all the people who are following us through the webcast. We know that there are quite a number of people from India and from different parts of the world who are following this conference live. And so it is live now, but also the video will be available on demand. So there will be a link on the UNESCO website and then maybe different pages where you will be able to either to see and to watch the entire conference, or the people who have not been able to attend today to follow that conference. But that being said, it's my great pleasure to introduce to you Manjul Bhargava. Professor Manjul Bhargava is a very well-known Indian, Canadian, American citizen who has received several awards, and the most famous one is the Fields Medal. And Professor Manjul Bhargava will tell us something maybe a bit uncommon and a bit surprising. He will be talking about poetry, drumming, and mathematics, of course. So that being said, you've got a small biography in front of you. So it's not the moment to give you the details, because it would be a very long presentation on all his career and what he has done. So you will find on your chairs a small presentation of Professor Manjul Bhargava. But he's a very, as you can imagine, a very famous professor. And we are very proud to receive him today, this afternoon at UNESCO. So, Professor, the floor is yours.
Can you hear me all right? Okay, well, bonjour and namaskar. It's a real pleasure to be back. You'll be tired of me by the end of the conference. So what I want to talk about in this session are some of the connections among poetry and drumming and mathematics. In school, when we learn mathematics, it's often taught as a subject in itself. Sometimes it's classified as a science. But what a lot of people don't know is that mathematics actually has many of its origins in the arts, in music, in poetry. And so a lot of ancient artists were doing incredible mathematics. And they didn't consider themselves mathematicians, they considered themselves artists, which really illustrates the fine line between art and mathematics. And so it's been one of my goals as an educator to get more young students interested in mathematics, not just through the sciences, but also through the arts. So the reason it happened to me, I actually got interested in mathematics through the arts. The reason it happened to me is that my grandfather was a scholar of Sanskrit and of ancient Indian languages and of history. And so a lot of what he taught me about the rhythms of Sanskrit and of Sanskrit poetry really resonated with me as someone who really enjoyed mathematics. So a lot of what I learned about mathematics was through the rhythms of Sanskrit poetry, and later on through the rhythms of classical Indian music. And those mathematical intricacies of these subjects is something that really inspired me to study mathematics, in particular the areas called combinatorics and number theory. So I want to tell you a little bit about a couple of the stories that really inspired me when I was growing up, that got me into mathematics, and something that I still use today, both in my mathematics and in my music. And so I'd like to tell you a little bit about that. I'll start with poetry. So what does mathematics have to do with poetry? That may surprise some people who aren't familiar in particular with poetry of Indian languages. So often in poetry, in any language, when you read poetry, there's a notion of being accented or not accented, right? There's syllables that are considered accented, and there's syllables that are unaccented. Sometimes they're called stressed and unstressed syllables. in Sanskrit there is a notion of stressed and unstressed, but it goes a little further. There's a notion of a syllable being long or short. A long syllable is called guru. A short syllable is called laghu. And what's special about the way that this stress and unstressed is done in Sanskrit is that long syllables are actually pronounced for a longer duration than short syllables. So when you pronounce a long syllable, it takes 2 beats of time. When you pronounce a short syllable, it takes 1 beat of time. So long syllable, when you read Sanskrit poetry, a long syllable you actually pronounce twice as long as you pronounce a short syllable. So Sanskrit poetry, like any kind of poetry, consists of syllables, each of which is either long or short, guru or laghu. And the key point here is that a long syllable lasts 2 beats of time when you pronounce it. A short syllable lasts 1 beat of time when you pronounce it. And so this extra structure on Sanskrit poetry immediately leads to all sorts of mathematical questions that the ancient poets considered in great detail. And you can start to imagine already what kinds of questions that might come up. Okay, so remember, a long syllable is 2 beats of time, a short syllable is 1 beat of time. Okay, and so here's a basic question that would have come up for ancient poets. Suppose you have 8 syllables, suppose you have 8 beats left in your stanza of poetry that you're writing. How many ways can you fill it up with longs and shorts? Okay, where a long takes 2 beats and a short takes 1 beat. Right? So if you have 8 beats of time left and you need to fill it up with longs and shorts, then how many ways can you do that? So, well, you could go long, 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 right? Or you could go short, 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 short. Or you could do various things in between, short, long, long, short, long, long, short, short, long, and so on. And so poets studied this in great detail in ancient times, going back a couple of thousand years. And so here's the basic question. If you have 8 beats left of time, how many ways can you fill it up with longs and shorts? Here are 4 examples that I just gave you. How many ways can you fill in 8 beats with longs and shorts? So you can do all longs, all shorts, but you can do many things in between. And the question is, in how many ways can you do that? Another question is, you don't just want to know how many ways you can do that, but is there a way of naturally listing them all, generating them in your head so that you can actually practice them, so that whenever you need it, you can use it? For a drummer, that's the basic question. When you're performing on stage and you're improvising and you need to fill in 8 beats with longs and shorts, you want to be able to do it on stage immediately. And so you need to know that repertoire of ways that you can fill it in. And so that's why this question goes back thousands of years. Okay, so let's try and figure out what the answer is to this. So how many ways can you fill in 8 beats with longs and shorts? Okay, of which these were 4 examples. Well, first of all, we can phrase the question more mathematically. Mathematically, what is the question we're asking? We're asking, in how many ways can one write the number 8 as the sum of 1s and 2s? Right? That's what we're asking. So long, 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 long was 2 plus 2 plus 2 plus 2. That was giving 8. And in general, the question is, if you have n beats left of time and you want to fill it in with longs and shorts, the question mathematically is, in how many ways can you write a number n as a sum of 1s and 2s? Right? That's the question that's being asked mathematically. That's equivalent to the question of asking, if you have 8 beats of rhythm left, how many ways can you fill it in with longs and shorts? Okay, well, let's work out a few examples. So suppose you just have 1 beat of time left. How many ways can you fill that in? Okay, you can just do short. That's it. There's no room for even a single long there. So just 1 way. Okay, you can just put a 1. Okay, so the total number of ways of doing that is just 1. Okay, but suppose you have 2 beats of time left. Then you can do short, short, or you can do long. Okay, so you can do 1 plus 1, right? That gives 2, or you can just do 2. Okay, so there are 2 ways, right, of filling in 2 beats. Okay, with 3 beats, well, you can do short, 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 short. You can do long, short, or you can do short, long. Okay, so there are 3 ways of doing it there. Okay, and you can similarly work out n equals 4, short, 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 long, short, 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 long, short, 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 long, long, long. 5 ways. Okay. And you can continue working those out. For n equals 5, there are all those ways of breaking it up. There are 8 ways. Okay, and now people see a pattern. Okay, so the pattern is 1, 2, 3, 5, 8. So what is the general answer? The ancients came up with an ingenious way to obtain the general answer. How many ways can you write n as a sum of ones and twos? Or how many ways can you fill in n beats with shorts and longs? And this was their method, written in poetry. Write down the numbers, so here's the translation of the poetry. Write down the numbers 1 and 2. And then each subsequent number that you write down will be obtained by adding the previous 2 that you wrote down. And then the nth number that you write down will give the number of rhythms having n beats. Okay, a number of ways of breaking up n beats into longs and shorts, the number of long, short rhythms, right? Long syllable, short syllable rhythms having n beats. That will be the nth number that you write down if you follow this procedure. So let's follow this procedure. So what do? We write down the numbers 1 and 2. There we go. And then the next number that you write down is the sum of the previous 2 that you wrote down. So 1 plus 2 will be 3, 2 plus 3 will be 5, 3 plus 5 will be 8, 5 plus 8 will be 13, 8 plus 13 will be 21, and 13 plus 21 is 34, 55, and so on. And what is the 8th number that we wrote down here? It's 34. And so the number of rhythms having 8 beats is 34. There are 34 rhythms having 8 beats, consisting of long and short syllables. Okay, so this is a method that was described in ancient times in India. They're called, by Sanskritists, these numbers are called the Hemachandra numbers, after the linguist Hemachandra, about 1050 AD, who first documented them and also proved their recurrence property. In fact, these numbers were studied even earlier than Hemachandra in India. They were studied by Pingala and Virahanka and Gopala. And then finally by Hemachandra, who actually listed all the numbers up to 34. And for that reason, Sanskritists have called them Hemachandra numbers, although they may even be named after people who came before Hemachandra. Of course, these are also known as the Fibonacci numbers in the West, after the Italian mathematician who lived about a century after Hemachandra. Okay, so there's a basic question here, which is why does Hemachandra's method work? In other words, why does that procedure where you just keep adding the sum of the previous 2 numbers, why does that give you the right answer for the number of rhythms having a given number of beats? And that argument, the reason for that is also given by the ancients. In particular, here's Hemachandra's argument. It's based on an argument that actually was given by Pingala in around 300 BC. His argument is very simple. It's given in poetry. It's just one line. He says, why is it true? Because every n-beat rhythm ends with either a short or a long. That's his whole argument. Okay, so what if you've read Sanskrit poetry, you'll know that there was a habit in ancient times to write things as succinctly as possible, because Sanskrit poetry was an oral tradition. So people wrote things as succinctly as possible. This is an entire explanation for why this works. So let's try to understand what this means. So every n-beat rhythm ends with either a 1 or a 2. Why does that mean that to figure out the number of rhythms having n beats, you have to sum the previous 2 things? Well, if you have an n-beat rhythm, it ends in either a 1 or 2. That's clearly true, right? It ends in either short or long. If it ends in a short, if it ends in a 1, then how many ways can you fill in the rest of the rhythm? Well, there are n minus 1 beats left. And so that's the previous number that you had written down. And if your n-beat rhythm ends in a 2, right, if it ends in a long, then you have n minus 2 beats left to fill. And so that's the number you had written down the time before. So the number of n-beat rhythms is equal to the number of n minus 1 beat rhythms, where you tack on a short, plus the number of n minus 2 beat rhythms, where you tack on a long. And that's why the method works. So that's kind of a one-sentence proof, which at first it seems surprising, but then once you understand the answer, it's a very, very elegant, what mathematicians would call a very elegant reason for why that method works. Okay. So what that means is, if you hn, h sub n, denotes the number of rhythms having n beats, then if you take those set of rhythms that have n beats, there are 2 kinds. Those that end in a short, in which case there are hn minus 1 ways to fill the rest, or An n-beat rhythm ends in a long, and then there are hn minus 2 ways to fill in the remaining syllables. So hn is equal to hn minus 1 plus hn minus 2, and that's exactly the relation we use to figure out the number of rhythms having a given number of beats. So a very beautiful argument, a very natural way of understanding the Hemachandra Fibonacci numbers. They come up in a very natural way through poetry. And in fact, that's the way they actually came up in history. So these Hemachandra Fibonacci numbers now form the basis of a huge mathematical and artistic theory. So of course, their origin is in poetry, of course. But they're used a lot in the visual arts. Lots of architects have found nice ways to use them in a visual way. But my favorite place where they come up, I was saying that poets were the first ones to find these numbers, but in fact, nature had known these numbers even before humans existed. So my favorite place where these numbers come up is, of course, in nature's art. So what happens is, of course, there are many other places where these numbers come up. There's actually a whole journal in mathematics called the Fibonacci Quarterly that's dedicated to just these numbers. That's how rich these numbers are. But let me tell you how they come up in nature's art. So if you look at daisies, it turns out that the number of petals on a daisy tends to be one of these numbers. So for example, here's a picture of a daisy. And how many petals do you see? 13, right? This daisy has 13 petals, which, as you know, is one of the numbers in the Hemachandra Fibonacci sequence. And if you look at, here's another picture of a daisy, and if you count the number of petals on here, you'll find that there are 21 petals. So the number of petals on a daisy tends to be one of these numbers. There are daisies that have 13 petals, there are daisies that have 21 petals. And this is my favorite picture. This is a picture of an entire garden of daisies. And it turns out that each one of these daisies has 34 petals, which I know because I actually sat there and counted all of them. So these all have 34 petals. It's amazing that they all know how to go to the number of rhythms having 8 beats. So the flowers go straight to those numbers, 34, in this entire garden. And it took a while for mathematicians and biologists to understand why daisies tend to have this particular number of petals. And it's kind of understood now, though not really fully, but it's understood in a mathematical way that has its origins in biology. It has to do with the fact that petals grow out of seeds that spiral out in the center, and the tightest way to pack seeds in the center, it turns out, occurs when each additional seed that's sprouted turns by what's called the golden angle. And that gives the tightest packing of seeds. And when you go around the spiral 8 times, and you count the number of petals, you get 34. So it's kind of understood now, and it's very, very beautiful mathematics and beautiful biology that dictates why this is an efficient evolutionary reason why they would want to have this number of petals. And so, of course, as I mentioned, as a musician, this theory is very important. If you have 8 beats of time left, a lot of the Indian music repertoire has been influenced by the ancient poetry. So a lot of the musical repertoire has mimicked the kinds of rhythms that occur in Sanskrit poetry and in ancient Indian poetry. And so a lot of times as a drummer, I might have to be sitting on stage. There are 8 beats of time left, and the theme at the moment is this dichotomy between long and short. And there are 8 beats of time left, and I need to improvise an 8-beat rhythm using just longs and shorts. And so I need to know how many ways I can do that, and I need to just be able to generate them. And then, so that's the mathematical aspect of what one needs to do as a drummer. But then, of course, there's the artistic aspect. Which ones of those 30? So I know there are 34 ways now, and I've practiced all of them. And now when I'm on stage, stuff has been happening on stage for a while, and I need to extract from those 34 the ones that I want to tell the story and fit the mood of that moment. And so a lot of improvisations happen by picking from those 34. And depending on how you pick from those 34 and how you emphasize the left hand and the right hand, allows you to express many different emotions, many different things, just by using those 34 combinations. So I wanted to play for you a short clip of Ustad Zakir Hussain, who at a moment where he's playing a solo and he's in this dichotomy between long and short, he wants to just play among these 34 combinations, just longs and shorts, 8-beat improvisations. Let's see. Longs and shorts, only longs and shorts this whole time. That's not longs and shorts. Okay. So that entire drumming clip, that was a minute long, and he's only playing longs and shorts that entire time. Just 2 phrases that entire time, and it's just expressing so much. He plays so many different things, and just by changing the emphasis, by repeating something, by changing one subtle thing, you're able to express a lot of emotion and a lot of variety just by longs and shorts, and that's a technique that's often used in the drumming repertoire of India. Let's see. Okay, so that's just one example. There's lots of examples like this. You can imagine that there are phrases that are long and short and extra long. You can imagine a lot of different variations. Here's another kind of variation that comes up for poets in ancient India, which is how many rhythms are there that consist exactly of n syllables? So now we're not paying attention to whether they're long or they're short. We're not paying attention to whether they're 1 beats or 2 beats. We're just paying attention to whether they're long or short. And we want an n total syllables. So how many rhythms are there that consist exactly of n syllables? Well, the answer is, well, there are 2 choices for the first one, then there are 2 choices for the second one, then there are 2 choices for the third one, all the way up to 2 choices for the nth one. And so there are 2 to the n possibilities for the number of n syllable rhythms. So now we're not talking about n beat rhythms, right? We're talking about n syllable rhythms. And the answer there is 2 to the n. So in ancient India, there were two kinds of ways that poets classified poetry. One was in terms of the number of syllables. One was in terms of the number of beats. Okay, we already worked out in terms of the number of beats how many rhythms there are. But if we were talking about the total number of rhythms having a given number of syllables, the answer is 2 to the n if you're asking for n syllables. Because each syllable has 2 choices. Right? Okay, but the next question that poets considered was the following. How many rhythms are there consisting of n syllables, where you specify how many short syllables there are and how many long syllables there are? So I want to make rhythms that have 2 short syllables and 3 long syllables. How many ways can I do that? Okay, so remember, short is called laghu and long is called guru. So we'll use L and G to represent short and long. So for example, let me just show you. For n equals 3, suppose I want to make a 3-syllable rhythm. Well, I could go guru, 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 right? G, 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 L, G, L, L, or L, 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 or G, L, G, or L, G, L, or L, G, G, or L, L, G. Those are all the possibilities to make a 3-syllable rhythm with a laghu and a guru. Now, if we want to break it up by how many G's there are, well, there's only one rhythm, right, that has 3 G's. That's over here. There are 3 rhythms that have 2 G's and 1 L. And there are 3 rhythms that have 2 L's and 1 G. And then there's 1 rhythm that has 3 L's. So if I wanted to count the number of rhythms that have 3 syllables, of which 2 are long, the answer is 3. Okay, so you see this kind of pattern, 1, 3, 3, 1. One that has 3 Gs, 2 that has 2 Gs and 1 L. There are 3 rhythms that have 2 Ls and 1 G. And then there are 3 rhythms that have, there's 1 rhythm that has 3 Ls. And the total, of course, 1 plus 3 plus 3 plus 1 is 8, which is 2 times 2 times 2, right, which is supposed to be the total number of 3-syllable rhythms. So in general, suppose I now wanted to know the number of 8-syllable rhythms that have 3 longs and 5 shorts. Okay, how would I figure out the answer? And the great Sanskrit poet and linguist Pingala goes back to 300 BC, gave a complete solution to this problem for general n. The complete solution was expounded a little bit later on by a commentator on Pingala known as Halayud. And here's the solution that they gave. So the general answer, it sort of comes about by the same idea. Remember I said that Hemachandra actually got his idea from an earlier poet, and that earlier poet was Pingala, who had actually solved this problem first. So here's the idea. It's very similar. Write down the number 1, and then each subsequent number that you write down is going to be obtained by adding the 2 numbers immediately above it. Okay, not the 2 numbers that you previously wrote down to the left, but the 2 numbers that are immediately above it. And what Pingala and Halayud write is that what results is a mountain of jewels. Meru Prastar. So, okay, so here we go. So we wrote down the number 1. Okay, now the next number we're going to write down is going to be the sum of the 2 numbers above it. So we're going to write down this 1. This 1 is the sum of this blank and this 1. Okay, and over here we're going to write a 1 as well. That 1 is the sum of this blank and that 1. Okay, let's do the next row. Well, this 1 is going to be the sum of blank and 1. Okay, the next number is going to be 2, which is the sum of the 1 and the 1, the 2 numbers that are immediately above it. Okay, and then what's this last number? That's 1. It's the sum of this 1 and this blank. Okay, and then the next line is 1, 3, 3, 1. This 1 is the sum of blank and 1. This 3 is the sum of 1 and 2. 3 is the sum of 2 and 1. 1 is the sum of 1 and 0. And then the next line is 1, 4, 6, 4, 1. And so on. And so that's the Meru Prastar, Pingala's Meru Prastar. It's a mountain of jewels because it's coming in this triangular shape. And the jewels are the numbers. So it's the triangular shape with these jewels that are on there, which are these beautiful numbers that tell you so much. And what do they tell you? Okay, so here's Pingala's Meru Prastar again. Notice those same numbers. Here's the 1, 3, 3, 1. Here's the 1, 4, 6, 4, 1. Okay, so how do you use this? Suppose you want to know the number of rhythms having 5 syllables that have 2 Gs and 3 Ls. Okay, so 2 Gs and 3 Ls, what do we do? So the total number of syllables is 5, so we go 1, 2, 3, 4, 5. Okay, and then how many Ls did we ask for? 2 Ls. So 1, 2. And so this here is the number of rhythms having 3 Gs and 2 Ls, is 10. Remember we had asked about the number of rhythms having 2 Gs and 1 L? Well, we go down 3, 1, 2, 3, and then we want 1 L, so we go over here. And so there are 3 rhythms, remember, that have 2 Gs and 1 L. And so in this, once you make this table, you can figure out the number of rhythms having any number of shorts and any number of longs. Okay, so if you want 7 longs and 3 shorts, you just go down 10, and then you count over 3, and you'll have your answer right in the mountain as one of the jewels. And that's the power of Pingala's Meru Prastar. And you can ask the same question, why does Pingala's method work? I'd like you to work that out, because it's the same reason, essentially. It's the same reason. Namely, that if you're trying to make an n-syllable rhythm, okay, so you can ignore these symbols if they don't mean anything to you. So if we use n choose k to denote the number of n-syllable rhythms having k short syllables and n minus k long syllables, okay, well, if you have an n-syllable rhythm, it either ends in a long or a short. Okay? If it ends in a short, then you have n minus 1 things left to, right, n minus 1 syllables left to decide with k minus 1 shorts, because you've already used 1 short at the end. If your n-syllable rhythm ends in a long, then you have n minus 1 syllables left to fill, but you still have to use k shorts. Okay? And so this element of the mountain of jewels is going to be the sum of the two that are directly above it. Okay, so I did that kind of quickly, but I'd like you to think about that. Why the same reasoning works to make the mountain of jewels as well. I discussed the Hemachandra Fibonacci example first because that one is much quicker to understand. But once you understand that, the slightly more difficult example you can also understand. So this is called Pingala's Meru Prastar. It goes back to 300 BC. And appears in the commentary in 1000 AD. So what are the applications? Well, the entries of the Meru Prastar are what are called binomial coefficients. And so they're actually one of the most important kinds of numbers in mathematics. They occur all through statistics and combinatorics and number theory and probability and pretty much every area of mathematics. And amazingly, they first came up, again, in poetry back in 300 BC and then in 1000 AD in the commentary of Halayud. So the origin, just like of the Hemachandra Fibonacci numbers, the origin of binomial coefficients is in poetry. Okay, so just to give you a recap. So counting rhythms and meters having a fixed number of beats, okay, if you fix the number of beats, that leads to the Hemachandra or Fibonacci numbers. If you count the number of rhythms having a fixed number of syllables, that yields Pingala's Meru Prastar, Pingala's mountain of jewels, which is also called Pascal's triangle. In the West, Pascal, after the French mathematician Pascal, who lived 2,000 years after Pingala. It's kind of interesting that these two kinds of numbers that I just told you about, right, the Pingala Hemachandra numbers and the Hemachandra numbers and Pingala's Meru Prastar, they're related to each other, those two kinds of numbers. If you look at Pingala's Meru Prastar there, and you sum along what are called the shallow diagonals, you sum the numbers along any shallow diagonals, you recover the Pingala Hemachandra numbers. And this is one of those things that mathematicians just love. You have two different problems giving you two different kinds of answers, and then they come together and you find that they were actually talking about the same thing, or they're related in some unexpected way. This is actually a fact that was written about by poets in ancient times as well. And they give a reason for it. And you can actually understand. So if you think about it, if you try to interpret all the numbers that are here in terms of rhythms, then you should be able to understand why this happens. And and when you do understand that, it's one of those moments that mathematicians love, where two areas come together in this elegant way, and they're related. So the mountain of jewels and the Hemachandra numbers, they're related by just summing along the shallow diagonals. You produce the Hemachandra numbers. Right, so 1 plus 5 plus 6 plus 1, that gives you 13 here. Right, and so here, the next one would be 21 and 34. And so you should try that out. That's very beautiful. Okay, so that's the story of counting rhythms having a given number of beats or a given number of syllables, two problems that were really considered in ancient times by poets who ended up discovering two of the most fundamental objects in mathematics. And they were the first discoverers of these fundamental objects. They were poets. Again, the fine line between art and mathematics. Here's another exercise for you. What happens if there are three kinds of syllables, okay, instead of two? Right? So there could be short, which is 1 beat. There could be long, which is 2 beats. And there could be extra long, which is 3 beats. Okay? We only had short and long before, but actually in Sanskrit there is a notion of an extra long syllable, which is called plut, which has 3 beats. And so what happens? Well, it turns out you get what are called the Threedimensional numbers, or the Fibonacci numbers. It's interesting that the same pun happens in both languages. So these numbers are made by summing the 3 previous numbers that you wrote down. And it turns out you can figure out why that is, for the same reason. Okay, that's if you count the number of rhythms having a given number of beats, consisting of short, long, and extra long. And you get a 3-dimensional Meru Prastar, a 3-dimensional mountain of jewels, when you're counting the number of rhythms having a given number of syllables, having shorts and longs and extra longs. So I really like this 3-dimensional Meru Prastar, this 3-dimensional mountain of jewels. it looks like this. So you can kind of see this is a three-dimensional array of numbers. The reason I like this is that, well, we live in a three-dimensional world. Our mountains are three-dimensional. And so here's a three-dimensional mountain of jewels. And you can see that each number that comes up in this mountain of jewels is the sum of the three numbers that are directly above it. So for example, this 2 here, if you can visualize this in 3 dimensions, this 2 here is the sum of this 1, and then this blank. That's right. This one might be easier to see. This 6 is the sum of these 3 2s that are directly above it. This 12 here is the sum of this 3, and this 6, and so on. And so now suppose you want to count the number of rhythms that have 5 syllables, okay, of which 1 is short and 1 is long, and 3 are extra long. How would you do that? Well, you'd start here and you'd go the first layer, second layer, third layer, fourth layer, fifth layer, okay, and you come over here, and then we said 1 short and 1 long, and so the answer is 20. There are 20 ways of making a 5-syllable rhythm, having 1 short, 1 long, and 3 extra longs. And so that's how you can use this three-dimensional Merupa star in the same way for three different kinds of syllables, in the same way that we did for 2 different kinds of syllables. So this is the three-dimensional Merupa star. In the modern world, these are called multinomial coefficients. And again, they also come up heavily in probability and statistics and every branch of mathematics. But the original motivation to talk about these was counting rhythms in poetry and in music. That's where multinomial coefficients also originally arose. Okay, so I want to tell you one last story, a mathematical story that originated in poetry and music. This is one of my favorite stories, one that really inspired me when I was a child. It's the story of this word that every Sanskritist knows, and every South Indian drummer in certain traditions of drumming in the South know. They all know this word, Yamato Rajabhana Salaga. So what's special about this word? What does it mean, first of all? It doesn't mean anything. It's just a sequence of syllables that everybody learns, but it doesn't mean anything. Okay, so why does everyone learn it then? The reason they learn it is in the sequence of shorts and longs that occurs in this word. So the longs have been indicated with the bar on top of the vowel. So it's Yamata Rajubhana Salaga. Okay? So if we use 0 to represent short syllable and a 1 to represent a long syllable, then if you know this word, then you know the sequence 0, 1, 1, 1, 0, 1, 0, 0, 1. Right? So if you memorize this word, Yamata Rajabhana Salaga, then you have memorized the sequence 0, 1, 1, 1, 0, 1, 0, 0, 1. The zeros corresponding to the short syllables that you're saying and 1 corresponding to the long syllables that you're saying. Okay, so why on earth would you want to do that? Well, there's something very special about the sequence of zeros and ones. And what's special about it? Well, if you look at the consecutive triples that occur in this word. So for example, the first consecutive triple is 0, 1, 1. The next consecutive triple is 1, 1, 1, right? The next consecutive triple is 1, 1, 0. Then 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. How many consecutive triples did we just do? That was 8. And they're all different. And how many possible triples are there? There are 8. Remember, 2 times 2 times 2. So this word sweeps out every single triple of zeros and ones exactly once as you sort of move your window from left to right. Right? Each consecutive triple gives you a different triple of zeros and ones, and every single possible triple is swept out exactly once. So that's a very special property of the sequence of zeros and ones. If you have to start somewhere. If you start with 0, 1, 1, it turns out there are only 2 solutions to that problem. If you start with 0, 1, 1, and you want to continue it so that you sweep out every possible triple exactly once as you move from left to right, there are only 2 ways that you can do that. And this is one that the ancients came up with. Another exercise, find the other one. Okay, but this is the one they chose. They chose to go with this, Yamato Rajabhana Salaga. And so every musician and every Sanskritist used to learn this word. And what is the reason for it? Okay, so everyone now has this common word that they all know. And so what do they do with it? Well, there's another special property of the sequence of zeros and ones, which you notice that it begins with 0, 1, and it ends in 0, 1. What that means is that if you consider that sequence of zeros and ones as a snake, this is the way that it's often been described, then the snake can eat its tail. If it eats its tail, then that 0 and 1 in its head will overlap with the 0 and 1 in its tail. And so here it is, going for its tail. Here's the snake going for its tail. And now, here it goes, it eats it, and you can see that these two zeros became a single 0, and these two ones, right, became a single 1, right? This is a single 0, and this is a single 1. And now what's happened in the sequence of zeros and ones here is that if you go along the snake and look at consecutive triples, right, so you have 0, 1, 1, and then 1, 1, 1, right, and then 1, 1, 0, and then 1, 0, 1, and then 0, 1, 0, and 1, 0, 0, and then 0, 0, 0, and then 0, 0, 1. As you go around the snake and take a window of 3 all the way around, you get every single triple exactly once around the snake. And that's had many technological applications, even in modern times. Okay, so what did the ancients use this for? Well, for them, and it's still used today by drummers and by poets, the word yields an efficient mnemonic for remembering long rhythms. So let me explain. How does it do that? Well, we have Yamata Rajabhana Salaga there. So ya, if you just use ya, you look at the triple that starts ya. Yamata, 0, 1, 1. Ya means 0, 1, 1, right? So, right, if you start at ya here, you have 0, 1, 1. Ma means 1, 1, 1, because if you start at M, you have 1, 1, 1, long, long, long. If you start at T, you have 1, 1, 0. So T can be used to mean 1, 1, 0. And so on. So each letter in this word, if you look at any consonant, you can use it to represent the triple that starts there. Okay? And each letter will therefore represent a different triple because of the property of the sequence of zeros and 1s that it represents. Okay, so let me give you an example. So how would you use this? Suppose you said the word tiramisu. That means a rhythm. Which rhythm does it mean? Well, T, what does T mean? It means 1, 1, 0, right? T means 1, 1, 0, right? Because in the word, it starts at the triple, T starts to triple 1, 1, 0. So T means 1, 1, 0. What does the R mean? Yeah, 1, 0, 1. What does the M mean? 1, 1, 1. Yep, because here ma starts 1, 1, 1, right? And then the S, yeah, 0, 0, 1, right? Because the S here starts sa le ga, 0, 0, 1. And so if you told your friend, if you both knew that word and you said to your friend tiramisu, you'd both think of this rhythm. And this was actually used, and it's still used by drummers in South India. So a lot of times if you go to a South Indian music concert, you'll see two artists meeting on stage for the very first time in their life. And suddenly they're playing these long and complicated rhythms in unison. How are they able to do that? Well, one might have just whispered a little sentence into the other's ear. And it's so ingrained in them, this translation from these letters to rhythms, that they unwind that into the long rhythm in the same way and immediately start to play it in unison on stage. And that's how they do that. So another example is Yosemite. These are not the kinds of words they would usually use. I just thought I'd give English examples. Okay, now here's an issue that could come up. What if you have your rhythm of zeros and ones, and you break it up into triples, and you assign each triple a letter using this word? That's all fine and good, but suppose your rhythm wasn't a multiple of 3 in length. You might have a singleton left over. What do you do with that? Well, notice that each of these letters starts a triple, but then these two last here at the end don't start any triple. And one of them is short and one of them is long. So you can use this la, which actually represents laghu, to represent a short that ends up at the end, and you can use ga to represent a long that ends up at the end. So for example, if you had terminal, the T means 110, the R means 101, the M means 111, the N means 000, right? And then the L here is just a singleton. A triple doesn't start there, so it just means short. And so if you wanted to write this rhythm as a word to tell your fellow player on stage, you could just say terminal. And you'd both know this long rhythm of length 13. Here's another example. If you have regal, what does the R mean? 101. And then you have 2 left over. The G means long, and the L means short. That's what you use. That's how you use these last 2 syllables. Just fill in when things are not a multiple of 3, then you can use those last 2. So the whole word encapsulates every possible rhythm that you could possibly write. Just by breaking it up into triples and singletons that are left over, you can use the last 2. And so this is a way of remembering long rhythms and encoding rhythms. And it's a mnemonic for long rhythms. So that's how drummers use it. But the way poets used it in ancient times is absolutely mind-blowing. And so I want to tell you how they did that. So here was an important problem for poets in ancient times. It's a mathematical problem, but it's really a problem of integrity. So poets in ancient times, they would often compose a new rhythm, okay, that had never been used before. They'd compose a new rhythm consisting of longs and shorts, and they'd wonder, how can I preserve this rhythm? I've composed this amazing rhythm. I want people to write in this rhythm, write poetry in this rhythm. How can I preserve it forever so that people always continue to play it the same way? So this was an oral tradition, remember. So people were going to transmit it from one generation to the next. And they wanted to preserve this rhythm so that it doesn't change even after many generations. Now that seems a very hard problem because you have a sequence of zeros and ones, you have a sequence of shorts and longs, and it's easy when you're telling, people have played the game of telephone, right? You whisper it into someone's ear, and one bit can easily be flipped. Any short could suddenly become a long, or a long could easily become a short. And after several generations, the rhythm doesn't look anything like what it was when it was originally composed. The ancient poems composed hundreds of original and beautiful rhythms, and they wished to preserve them without even a single error forever. How is that possible? Well, they figured out an amazing method by which hundreds of rhythms have come intact to us, and we can be sure they haven't changed for thousands of years. And so how did they do that? Well, they knew that this task would be difficult, especially if these rhythms were to be transmitted orally from generation to generation. They came up with an ingenious method to this problem, which is very mathematical and very poetic. They used the word Yamato Rajabhana Salaga in an incredible way to preserve their compositions forever for posterity. And so let me explain how they did that. So as a result, 3,000 years later, we still have their compositions intact, just as they had composed them. So you can think about this problem just for a second. How could one possibly do this if it's just being transmitted orally from one generation to the next? How could it be that the rhythm doesn't change at all? Okay, well, let me tell you what they did. So suppose you're a poet and you composed a new rhythm. Here's what you would do to make sure that it's preserved forever. What you would do is you would write a poem about your rhythmic composition. Okay, so you have a rhythm, you'd write a poem about the rhythm. And that poem would have the property that it's written in the rhythm that it's writing about. Okay, so you're going to write a poem in that rhythm about the rhythm. That poem will describe how many syllables are in your rhythm, how many longs and shorts. It's going to name the rhythm, it's going to give the rhythm a name so that everybody can refer to it forever by that name. And finally, okay, that already is an acrobatic task, right? You're writing a rhythm about the poem in the rhythm with the title, with the name of the rhythm, and a description of how many longs and shorts. All those things are in the poem. And then it has the additional property that it's encoding. Remember, we had a way of encoding the rhythms, right, by breaking it up into triples and using that mnemonic, where each triple had a corresponding consonant attached to it. That should also appear in your poem. the coding for the rhythm. If you were able to do all those things, then there's no way that the rhythm could ever be lost. Because if someone took that poem and changed any one thing about it, you'd notice the error, because it wouldn't all match up. Right? If you changed one short to a long, it wouldn't match the code, which is also contained inside the poem. So let me give you an example of this. Here's a very famous rhythm called Shardul Vikriditam. The translation is that if there are 12 plus 7 syllables in the form ma sa ja sa ta ta ga, then it is known as the play of the tiger. So this rhythm is called the play of the tiger. And it's in the form ma sa ja sa ta ta ga. Okay, that's the encoding of the rhythm. And the poem, in fact, is written in that rhythm. So here's the poem. This is the poem here. So I'll put the ones and zeros. So this means long syllable, long syllable, long syllable, short syllable, short syllable. So the rhythm is 1, 1, 1, 0, 0, 1, and so on. And the poem, so this is the rhythm that the author wanted to preserve, called the Play of the Tiger. And he wrote this poem about it in that rhythm. And his translation tells you that the poem is called, the rhythm is called the Play of the Tiger. And so it sounds like this. Suryashvei adima sajo satatgah shardul vikriditam. And we can, let me clap it for you so you can hear the rhythm. Suryashvei adima sajo satatgah shardul vikriditam. And so that's the rhythm. Maybe we should try it. Or, if you want to try clapping it. Okay. Ready, set, go. Not bad. So that's the rhythm that was composed in ancient times. And so what does this poem mean? It means that if there are 12 plus 7 syllables in this form, that's known as the Play of the Tiger. So here's the ma sa ja sa ta ta ga. Here's the encoding of the rhythm in the poem. Okay, now what does ma mean? Remember, I've put down the magic word down here so you can work this out. So what does ma mean? What triple does it mean? 1, 1, 1. And look, the poem starts 1, 1, 1. What does sa mean? Sa means 0, 0, 1. And here it is, 0, 0, 1. And so if you unwind this entire thing inside the poem into triples, it goes and covers the whole poem. So that's a real acrobatic feat. And once you've accomplished that acrobatic feat, if somebody changed this letter here and made it long, you'd notice, because when you unwind this encoding here, you'd find that, oh, it doesn't match, and you'd be able to fix it. So this is what in modern times is called an error correcting code. It's not just an error detection code, but it allows you to actually fix errors. If there's a mistake in transmission, you will catch the error because you know what properties this poem has, where if you unwind this encoding, it has to cover the entire poem. So for this reason, these compositions, and there are hundreds of them like this, that have been preserved for posterity forever, for thousands of years. And these are really magical, acrobatic poems that really requires clever composition, not just mathematically, but poetically. I'll give you one more example. This is another famous rhythm. It's called Bhujanga Prayatam Chaturbhiryakare. And it translates to, the gait of the cobra consists of a quadruple of yas. So here's a sequence of longs and shorts which you read this in. Bhujanga prayatam chaturbhiryakare. Right? 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. You want to try? Okay, we'll try this one. Ready, set, go. Okay, that one was easier, yeah? So it's just 0, 1, 1, 4 times. And it's called the gait of the cobra. The reason it's called the gait of the cobra is that when people saw cobras in ancient times, they found that they didn't quite go evenly back and forth. They'd kind of have jerks if you've seen a snake moving, right? And that's capturing the motion of a snake. So it's called the gait of the cobra. Now, it looks like 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. The encoding for this, remember, Yamato Rajabhana Salaga, what is 0, 1, 1? It's just represented by ya, right? Because starting at ya, you have short, long, long, 0, 1, 1. But if the poem you wrote about the gate of the Cobra had ya, 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 ya in it, that wouldn't fit in the rhythm. So how do they get around that? They made it a quadruple of yas, and that there, chaturbhir yakare. That allows you to say ya, 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 ya in the right rhythm to fit inside the poem. So this required a lot of poetic acrobatics. You have to find ways of saying things so that they fit in the rhythm. And once you got it all to fit, all these mathematical parts to fit, then it would never change forever. And so here's another poem that's come to us, never been changed. So this is perhaps the very first and very sophisticated use of error correcting and detecting codes in history. So just like the Hamish and the Fibonacci numbers and binomial coefficients, these fundamental objects in probability and statistics came up first in history by poetry. For the same reason, poets wanted to preserve the integrity of their compositions. And that's why error correcting and error detecting codes first arose in history as well, through poetry. And these are things that are not well known. They're well known to Sanskritists and to drummers in India, but they're not well known. And now, of course, these have become very fundamental objects in mathematics and in science. When we're having phone calls, we want our integrity of what we're saying to be preserved. And again, error correcting codes and error detecting codes are what are used. There are lots of other applications. There are searching algorithms in technology that use exactly this word, Yamato Rajabhana Salaga, and modifications of it. Remember the snake that had zeros and ones in a circle? So there were dials that were made in the earliest 20th century for dimmers, for lights. And how do you tell when you're rotating your dimmer? How does the mechanism know how much you've rotated it? Well, if you have a sensor that detects the on and off switches for just 3 consecutive things, that's enough to tell the position of the dimmer, because every triple along the dimmer is different, because it's arranged in Yamato Rajabhana Salaga. And so that was an early application of Yamato Rajabhana Salaga, is just to be able to tell the position of a circle just by having a sensor sensing the on and off switches just in a small range on the side, just a triple. And so that kind of idea was then used in codes on NASA missions. If you wanted to know the position of a satellite, where you had lots of zeros and ones, ons and offs switches going all the way around it, you only had to see one side of the satellite to be able to know what the position is, because every sequence of zeros and ones is going to be different, going all the way around. And so that's been used by NASA as well. And then finally, there are applications to card tricks. My advisor in college was Percy Diaconis, who was an amazing magician, who saw this poetic composition, Yamato Rajabhana Salaga, and thought, oh my gosh, this could totally be used for a card trick. Which is something, I should probably stop though. Huh? I could do a card trick. We could turn off the, yeah. Okay. All right, let me show you how it's done. It'll only take a minute. So I have here a deck of cards. So this is a trick that was invented by Percy Diaconis, the great magician. And so what I want to do is just take this deck of cards, and maybe I'll just take 5 people. Should I do that over there? Maybe they'll do it over there. So what I want to do is just cut the deck. Just cut the deck. So what I'll just cut, and then what I'll do is I'll have you each take the top card. Okay. And I'll leave this deck with you so that nobody suspects that I looked at anything. Okay, so you 5 I gave cards to 5 people, I think, right? You, and you, right? 5 of you. Okay, so what I want to do is I want to try to figure out your cards. Okay, so this is what my magician advisor told me. This sounds strange in an academic environment, but what I want you to do is concentrate on your card. Okay, you're concentrating, yeah? You gotta try to send me waves and make me... No trading of cards. Okay. Okay, I'm feeling something. But you know what? I feel red better than I feel black. Could the people that have red cards, could you stand up? So you two have black cards, huh? You're sitting down, you guys have red cards. Okay, I'm gonna try to guess the red cards first. So I need to try to, these lights are so bright that it's hard to do face reading. All right, I'm gonna try to. Okay. You're a red card. I'm gonna try to figure you out. You look like you have a small card. And you're a red card. It's a heart. Small heart. Is it 3 hearts? Yes? You can show it to everybody? You can show it up in the camera. All right, let's see. You, I think, have 7 of diamonds? Yes? You can hold it up. Okay, and you're the last red card. I think you have a 5? 5 of hearts? All right. Okay, now the black ones are more difficult. I don't feel black as well, but I think you both were giving, let's see, 5. You have a 5 of spades. Yes? All right. Let's see, do you have, I still have to tell your card, huh? Do you have a spade as well? 6 of spades. All right. So I want you to think about, so everyone understood how that happened, right? No? Well, this of course has to do with mathematics, and in fact the mathematics that I told you about today. This is on video, so magicians would be angry if I really said exactly how it's done. But I have said, I can tell you this, that I have told you enough today. This does use some of the ideas of poetry that came up. This is how the trick was first invented and inspired. So you know enough mathematics now to actually understand this trick, and I want you to go home and think about it. And if you figure it out, don't tell anyone. And so, yeah, thank you very much for your attention. I'll stop here. Thanks so much. Thank you.
Absolutely fascinating. I did not understand exactly what happened, but it's really fascinating. Well, I think we've got a couple of minutes to ask some questions to Professor Bhargava. Who has the question? Where was the trick or something like that? I mean, we've got microphone. Can we give the microphone? Yes, here is with you.
Hello?
Yeah, it works.
It works? Okay. So have you constructed yourself some of these self-referential poems that you told us about?
I have tried to make such poems. It's pretty hard. So I haven't done it so much in poetry, but of course, you know, when I learned these things as a child, the idea of self-reference is a very important one in mathematics. And so learning it from poetry actually allowed me to be so familiar with it as a child that I've continued using it in my mathematics, I'd say. You know, in my mathematics work, the idea of self-reference has been a powerful tool in proofs. And so I think more of my self-referential constructions have happened in my mathematics, I'd say. Yeah. But that's one reason that I really think it's such a great way of learning. That you learn, if you're more artistically inclined, learning about these kinds of ideas through poetry, through music, can be wonderful. And then when you go into mathematics, when you go into science, these same concepts actually apply there in the same way. And for me, that's been very helpful. And so, yeah, so I've definitely used the ideas that I learned from these poetic constructions. Yeah.
Good. Yes, we've got another question there in the front. Microphone is with you. Behind. Yeah.
This rhythmic thing, is it valid for all the languages, or it is only for the Sanskrit? Because
yeah, that's a great question.
Each language has different connotation. They've got different type of syllables. So how does it fit into other languages apart from Sanskrit?
Right. So when I was talking about the number of rhythms having a fixed number of beats, that's something that's very specific to Sanskrit because of the property that stressed syllables take 2 beats and unstressed syllables takes 1 beat. So that's why it's very special to Sanskrit and other Indian languages as well. Marathi has the same property of long and short being 2 beats and 1 beat. Kannada has the same property. So there are a number of Indian languages that have the same property. And so this word is actually learned by poets in all those traditions. But it doesn't, that kind of thing does not appear in languages outside India. So that's something that's very special. And maybe one reason why the Hemachandra Fibonacci numbers were first discovered in India, because it naturally came out of the structure, this mathematical structure of the language and the pronunciation. But for some of the other things I talked about, like counting the number of rhythms, counting the number of poetic meters that have a given number of stressed and unstressed syllables, that of course could be adapted to any language, and those same counts would still apply. But poets really started to think about it around Indian languages because of the mathematical way in which the language is structured and the mathematical way in which the poetry is pronounced. That's why it really happened with Indian languages first, for that reason. Yeah.
Thank you. Professor?
So, Professor Bhargava, it is often said that
thank you.
two kinds of mathematics, pure and applied. Now, you've created some of the best kind of mathematics, pure mathematics, and yet you seem to play with the applications a lot.
Mm-hmm.
So when you do mathematics, what is the balance between pure and applied? I mean, do you start from the applied and go to the pure, go from the pure to the applied? How does that work for you?
Yeah, so there are two kinds of mathematicians out there. They're called pure and applied. And that doesn't mean that both kinds of mathematicians don't work on both things. But for pure mathematicians don't look at the applications before they start working. Instead, they work on whatever they find most beautiful, most exciting at that moment. And history has shown that the most applicable mathematics has been that mathematics that mathematicians found just by pursuing beauty, pursuing exciting, pursuing the most, just following their nose and seeing what is the most exciting path that I can take. And just looking for that simplicity and elegance and beauty has led to some of the best, most applicable mathematics that's out there, even though those mathematicians who came up with it were not looking at the applications when they came up with it. So number theory is a great example. When people study properties of the whole numbers and the prime numbers, originally mathematicians just studied that because it's just so pretty. The prime numbers are just incredibly beautiful. They're the atoms of the universe of whole numbers. Every whole number can be expressed uniquely by multiplying together prime numbers. Like 18 is 2 times 3 times 3, and that's the only way that you could break it up into these atoms, these prime numbers. And so number theorists would study these things since ancient times, and they never thought that it would have an application. They were just studying it for its beauty. But now, of course, prime numbers are the most important tool in cryptography. So in cryptography, when you put your credit card number over the internet and you want it to be secure, prime numbers are essentially used, and the properties that have been developed over thousands, over the centuries, those properties of prime numbers are now used for encryption. And if that problem was just given to you, I need an efficient way of encryption, how would you ever think, oh, let me define prime number and do it? That repertoire of mathematics about prime numbers was there, just ready to be used. And that's what pure mathematicians do, is develop a repertoire of beautiful mathematics, simple mathematics, elegant mathematics, so that it's ready to be used for applications when the societal need arises. Of course, there are also applied mathematicians who do amazing things, and what they do is they look at the application that they need solved, and they look at the repertoire of pure mathematics that's there, to see whether anything from there will apply. They look at the repertoire of applied mathematics and see if anything can be borrowed. Or they take that applied mathematics problem and turn it into a pure mathematics problem and then try to solve it. So there are those two approaches. And they've both worked very well over history. And it's really clear that you really need both. Because there are many applications where if you were just thinking about the application, you would never have come up with that mathematics. But because people were thinking about it just by pursuing beauty and elegance and wonderful patterns, that they were able to come up with that mathematics. And so that's why pure science and pure science research is so important, to build that repertoire of fundamental science so that it's available when you need it.
Yes, maybe a last question. Yes? So, just at the back.
It was nice to see.
Just wait the microphone.
Hello, Professor Manjul.
How are you?
It was nice to see the familiar concepts which I knew as Fibonacci series and other ones coming up in ancient Indian poems. Are there instances of theorems or concepts which are perhaps not well known in contemporary mathematics, which appear in those ancient concepps?
Yeah, many. So I talked about a number of them today, but of course there are many others. There are lots of geometrical theorems that have been written in poetry because people wanted to make beautiful art. They were trying to. So the Pythagorean theorem is one theorem that comes up in ancient India before Pythagoras. So by Sanskritis it's called Bodhayan's theorem. Bodhayan again wrote in poetry in short stanzas explaining geometrical theorems that could be used to draw interesting diagrams for altars that were made at the time. So mathematics has really appeared in ancient India in a way that has kind of been forgotten. It's not really taught in school anymore, but in really beautiful ways from the artistic side. And what I gave today is just a small sampling, but there are many other instances. Yeah. And hopefully gradually we'll be able to bring them out again. I mean, this is the way that people used to learn. And I was lucky to have been able to learn that way because my grandfather had this great collection of Sanskrit works on his shelf. And I didn't like to go to school, so I would just stay home and look at his books. And I learned a lot of mathematics that way. And then I'd go to school and see that, see these theorems coming up again. And I'd be surprised that they were named after someone else, first of all. And also that they were taught in a actually much more boring way. I mean, if you get to learn it through art and poetry and drawings, it was a lot more fun for me. And so that's why I hope that we can bring it back into schools, at least learn it from that way too. That should be an option for those who are more artistically minded to learn science.
Thank you very much, Professor Manjul.
Thank you so much. Appreciate it.
You gave us some brilliant ideas about mathematics, but also about poetry, about art, about beauty, and also about education. And I think all these concepts, science, culture, education, are really at the heart of the mandate of this house, of UNESCO.
Right,
so
right.
you are really at home, and it was a pleasure to welcome you today. Thanks again.
Thanks so much. Thank you so much.
So the next session will start at 4. There is now a short break for tea or coffee, and you are welcome to come back at 4 for high-level segment. Thank you.